Quantum mechanics was the theory that resulted from the study of very small particles. Its successor, quantum field theory, developed ultimately from the study of the interactions of these particles. What we'll see in this discussion is a common move in the history of science when we think about the redefinition of reality that accompanies scientific progress. We begin by defining reality in terms of objects, things, entities. We learn about these things by looking closely at them, figuring out how they work, what they're made of, how they change. We then complicate matters by putting these objects together and examining their relationships. We have to enrich our picture of reality, our metaphysics, by now including aspects of reality that can't be found by examining the objects individually, no matter how close. So consider the notion of force, for example. If you have one object, you could determine that it has mass. But you would not come to see the existence of a gravitational force deriving from that mass unless you had a second object for it to act upon. Once we have multiple objects placed in physical relationships, new aspects of reality emerge. But the third step is to move to a holistic account, wherein the objects and the relationships are replaced by a larger vision of reality. In this larger version of reality, there's a single whole in which objects and relationships are embedded. It's this entirety that's seen to be the ultimate state of reality. Now, we saw this movement in the transition from Descartes, who begins with physical masses that behave in certain ways according to certain mechanical rules, such that all motion requires physical contact, pushes, pulls, twists. It's the only way we could get something to move. We then see in Newton's theory of universal gravitation the emergence of a force that imputes action at a distance. Objects pull gravitationally on each other based on a relationship between them. And that relationship, gravitational attraction, becomes something real, independent of either object. Now, Einstein came along and not only gave new mechanical laws to replace those of Newton, but a whole new gravitational theory. His theory replaced Newton's idea of space as fixed, unchanging, and never interacting with the objects in it. Einstein brought us to a new view of space, a dynamic, flexible thing that was always warping with the distribution of mass and energy and changing the way light and matter move in it. This undulating substratum is what physicists call a field. The concept of the field, occupying a central place in the general theory of relativity, the picture of the universe, changed into one in which we ceased to have individual objects relating to each other gravitationally, giving us instead a single holistic picture, a universe in which everything is always interconnected. In this view, the whole universe needs to be understood as a coherent single entity. Einstein adored the writings of the 17th century philosopher Baruch Spinoza. Spinoza was a pantheist. He believed that all that existed was a single substance. God was not some entity distinct from the world. God is the world. Everything we think of as individual things are not really discrete objects, but just modes of the whole, aspects of God. Spinoza's God does not sit outside the world acting upon it. Rather, since God is the world, all changes must come from within it. But these changes occur according to fixed laws, the absolute laws of logic. God has no free will. God cannot choose what to do. God is the slave of logic. Both Jewish and Christian clergy found that a bit troubling, and the view ended up making Spinoza's life kind of difficult. But Einstein, when asked by a rabbi if he believed in God, responded that he believes in the God of Spinoza, by which he meant that he thought that the universe is a coherent whole. All that exists is the field, a single unified entity that behaves in a completely deterministic way according to rational rules the human mind can discover. Einstein shared Spinoza's adherence to determinism, and this is why he objected to quantum mechanics. But the development of quantum mechanics proceeded along a similar path with respect to a holistic approach to the universe. To get there, let's start with another story involving Einstein. The main character, however, and he was indeed quite a character, is the Frenchman Louis de Broglie. Despite the fact that the monarchy in France had been long gone, de Broglie was quite proud of the fact that his family was noble, and on the death of his older brother, de Broglie would have inherited the position of Duke. He thereby demanded that everyone refer to him as Prince Louis Victor de Broglie. He was never at a loss for self-confidence. This trait would help him become an important player in the history of science. As a young researcher, he came to realize something quite straightforward and yet incredibly strange and deep. Now, in 1924, the air was full of talk about the two major discoveries in science. One was Planck's quantization of energy from black bodies, such as that for a single proton, E equals h nu. This was the basis for wave-particle duality of light. Light could be considered a particle or a wave, and there were physical tests that demonstrated both aspects. The other was Einstein's theory of relativity, according to which E equals mc squared. Mass, Einstein famously said, was just another form of energy. And with other forms, there should be ways to convert this energy back and forth, creating and destroying mass, as long as the energy in total is conserved. De Broglie thought, energy is energy. It's something that just changes form. We can turn electricity into heat, heat into chemical reactions like making water into steam. Steam can then be used to power an engine that does mechanical work. Mechanical work can lift an object, giving rise to gravitational potential energy, and so on. So, energy is energy. It moves from form to form. Now, Planck says that E equals h nu. Einstein says that E equals mc squared. E, the energy, can change from form to form, so then it ought to necessarily follow from E equals h nu and E equals mc squared that h nu equals mc squared. Simple middle school algebra. But the simplicity hides deep ramifications. In the middle of h nu equals mc squared is an equal sign. That is, the left side is just another way of saying the same thing as the right side. But on the left is nu, frequency. Only waves have frequencies. On the right is m, mass. Only particles have mass. Again, remember that particles and waves seem like completely different things. A particle is an independent object, an entity unto itself. It doesn't need anything else to exist. It is its own reality. A wave, on the other hand, is a disturbance in a medium. Think again of the college football fans doing the wave. Again, we see the wave move from section to section, but the wave is not a thing. It's just the fans standing and sitting in rhythm. In an empty stadium, there can be no wave, and when it appears, nothing new has been created, and when it peters out, nothing has been destroyed. Everything that had existed still exists. The contents of reality are unchanged, whether there's a wave or not. What de Broglie did by joining the two iconic equations of the turn of the 20th century is to assert that the strange particle-wave duality we attributed to light would also hold true for matter. Matter, if this were true, would have to be thought of as a wave. But waves aren't things with independent reality. My pen is not a thing, but a wave in some underlying medium. And it's not just my pen, but my body, the sun. Everything would cease to be independent elements of reality. De Broglie submitted this as his doctoral dissertation at the Sorbonne, the most prestigious university in France. His examiners rejected it for two reasons. First, it was so revolutionary, it couldn't be right. Second, it was so short and so simple, surely it didn't rise to the level of a doctoral dissertation. So, de Broglie sent it to Einstein. Einstein was impressed, and with Einstein's backing, this short, simple idea not only earned de Broglie his PhD, a few years later, it got him the Nobel Prize and led physics into a completely new direction. This gives rise to what physicists call quantum decoherence. If I have two electrons that bounce off of each other, then classical we think of the interaction like a game of billiards. The cue ball hits the 8 ball, the cue ball goes off in one direction, and the 8 ball hits two rails and falls into the side pocket. That's how I paid for college. But in quantum mechanics, All we can know is that 2 electrons went into the interaction and 2 came out. There is no sense of identity throughout the collision. If Ted and Carol are the electrons going in, there is no way to say which is which coming out. There is no identity here. 2 go in, 2 go out. That's all we can know. The problem, of course, is that self-identity is the most basic property of thinghood. Something is an entity, is a real object, if it retains its identity over time. You are who you are because you are the same person who experienced all of the events in your life. If we surrender identity over time, then we give up on the existence of things. And surely reality is made of things, right? Following de Broglie's result, physicists worked tirelessly probing the structure of the atom, and the results were surprising. Right? Rutherford had shown that the atom was largely open space with virtually all the mass focused in the central nucleus. Since atoms were electrically neutral and electrons were negatively charged, the nucleus must not only be massive, but also positively charged. Since we knew that the nuclei of light atoms like hydrogen and helium could be stripped of electrons and the nuclei isolated into beams, we knew there were particles called protons. But when we added up the masses of the protons and the electrons, the atom was heavier than our result. There was something else heavy inside the atom. Further, we knew that elements come in what we call forms, what we call isotopes, right? Same number of electrons, same number of protons, but different masses. Since the mass of the atom is in the nucleus, and all the isotopes are electrically neutral, there had to be some other sort of something in the nucleus adding that extra mass, something that contributed to mass but not charge, and we called them neutrons. Eventually, the neutrons were isolated and we observed them decaying. What popped out? An electron and a proton. Electrons are negative, protons are positive. If they get too close, then the charge ought to bring them together into a single electrically neutral object. The combined mass matched what the neutron had to weigh, given the atomic masses of our various isotopes, but there was a problem. We had conservation of charge, energy, momentum, but not what physicists call angular momentum, a measure of spin, which had to remain constant overall. So a third component was proposed to account for the discrepancies before and after the decay. A piece with no charge and virtually no mass. The Italian physicist Enrico Fermi called it a tiny neutral thing in Italian, neutrino. The neutrino complicated matters. See, when there was a simple heavy positive, light negative image of the atomic world, but the neutrino now suggests that the subatomic realm was more complicated, and physicists began to see what this subatomic world looks like. Here's where a second and third problem emerge. If the nucleus is as small as we found it to be, and if it's populated by protons, which share the same positive charge jammed together tightly, how does it remain stable? Like charges repel, and the closer they get, the stronger the repulsion. Nuclei should blow themselves apart because of the electrostatic force between the protons. The only forces we knew of were gravity and electromagnetism, and neither could explain it. The gravitational force is way too small, and there should be no electrical attraction, right? They're like charges. There must be some other force. The third problem concerns the neutron. Electrical charge explains how the proton and the electron stick together in making a neutron, but what about the neutrino? There has to be some sort of force that acts on the neutrino, and it would have to be different from electrical charges, since it's neutral, and gravity, since it's so tiny, virtually no mass. So there must be some other forces active at only minuscule scales, but incredibly powerful. The force that binds the protons to the protons would have to overcome the electrostatic force, and must be the stronger of the two and active only in the nucleus, since we see it nowhere else. So it was called the strong nuclear force. The one that exposes itself where the neutron breaks down to spit out an electron and neutrino, we call the weak nuclear force. So, what started out as a simple picture of reality with two forces, gravity and electromagnetism, and two basic components, electrons and protons, has been exploded. We need more forces and more particles. Well, how complicated is it? What had been a neat, tidy little universe was getting messier all the time. Now, science requires not just theorizing, but observing. For large objects, like my pen, right, we look at it by bouncing light off of it and observing that light with our eyes. What's absorbed and what's reflected tells us about the thing. But for subatomic particles, we can't do that. For big things, the light bounces off them or absorbs into them with an energy so small in comparison that it hardly affects them. But with things as small as parts of atoms, the light not only doesn't bounce back in the same way, the amount of energy the light brings overwhelms the system, changing it, scattering the particle in the light. We need a different way of seeing that doesn't involve directly seeing. We found this with particle accelerators. Now, to see subatomic particles, we need first to isolate them, free them from the nucleus, and then have them react with something else in such a way that the reaction has detectable properties. Detectable properties that we can use to learn things about their nature. The particle accelerators do exactly what they say. They accelerate particles. By giving the particles more energy and then banging them against hard things or against each other, we can cause them to break apart. If we have this happen in an area that's humid, the particles will leave trails like jets flying across the sky. Add a controlled magnetic field, and those vapor trails will curve. The greater the charge, the tighter the curve, with positive charges curving one direction and negatively charged particles curving the other. By accelerating the particles to extremely high energy, the resulting collisions revealed a wealth of particles form, many of which we don't generally see around us. Now, throughout the 1950s and 60s, new particle discoveries were regular occurrences, and it left physicists somewhat concerned about the proliferation. But they did what physicists do best and figured out how to categorize all these particles in such a way that clear classes emerged and underlying structures revealed themselves. Ultimately, this led to what we now call the Standard Model, which was put in its mature form by Americans Sheldon Glashow and Steven Weinberg and the Pakistani Abdus Salam. According to the Standard Model, there are two groups of particles, fermions and bosons. Fermions make up the particles we see in the atoms, as well as others formed by banging those parts together. Fermions come in two classes, leptons and hadrons. Leptons are bits that don't break down any farther. They're elementary. These include the electron, the muon, and the tau. Each lepton has an antiparticle, which is identical but for the charge. The electron's antiparticle, for example, is the positron, which looks just like the electron, except that it's positively charged. Additionally, each lepton has an associated neutrino and antineutrino. The remaining fermions are the hadrons, and these are made up of quarks. Remember that leptons don't break down any farther, hadrons do. Quarks come in 6 varieties, 3 pairs, up and down, top and bottom, strange and charm. Quarks and their associated antiquark can join together to form a meson. We get the pion, the psi, and the upsilon mesons. But usually they come together in triplets, what are termed baryons. Now, there are 14 of these baryons, the most famous being the proton and the neutron. The theory that baryons are comprised of quarks was originally formulated by the American Murray Gell-Mann, who intended to use the word quark, but being in the habit of regularly reading James Joyce's Finnegan's Wake, he came across the phrase, 3 quarks for Muster Mark. And since baryons are made up of 3 quarks, the reference was simply too perfect, and he changed the pronunciation and thereby the spelling to quark when he finally got around to writing the theory down. Breaking things down to their most elementary bit, from the 6 quarks and the 3 leptons, we're now able to build up all of the particles we see. But those particles interact, and the theory accounts for the interaction of particle on particles in terms of the exchange of other particles called bosons. Bosons are named after the Indian physicist Satyendra Bose, who, along with Einstein, first worked out the mathematical rules they obey. Now, there are 4 gauge bosons, which carry the various forces between fermions. The most famous is the photon, or light particle, which carries electromagnetic force between particles. Light is thought of as a thing, as a particle, a quantum of electromagnetic energy which is emitted by and absorbed by fermions, or collections of them. This is how forces allow particles to act on each other. Notice how radical a shift this is. We used to think of forces as sort of magical relationships between particles acting on each other over a distance. If you had two positively charged objects, they would repel each other. But what's doing the pushing? You could wave your hand in between them and not feel a material thing connecting them. Your hand wouldn't disturb the force. But now we see the four fundamental forces as the result of an exchange of gauge bosons between the particles. In this whole scheme, there was one element left out. One remaining boson that was trouble for the model, the Higgs boson. It was named for the British physicist Peter Higgs, was among the first who first proposed it. The Higgs boson was required to give mass to those particles that possess it. It was a latecomer to the Standard Model and only proposed as a fix for situations where the model gave deeply problematic anomalous results. But if this boson was added to the mix, everything worked out smoothly. The addition of it allowed physicists to predict other particles that had not yet been seen. And on this basis, they set off to find it. The confirmation of the Higgs boson being the last untested element of the Standard Model, it took years. But in 2012, 48 years after it had been predicted, the physicists at CERN, the massive accelerator based in Switzerland, announced they had found it. Being a neutral particle, Switzerland was an appropriate place for the Higgs boson to be found. Now, with the confirmation of the Higgs boson, the Standard Model had been accepted and nearly a complete account of the physical world. This language and the accompanying mental picture are problematic. Right? The usual way of talking about the Standard Model makes us think of the subatomic world as being composed of uncuttable particles, the classical Greek atoms. But recall that this is coming out of quantum mechanics. Right? We can think of particles because we're talking about quantized elements, but elements of what? Here's where we return to de Broglie. Recall that according to him, we need to see not just light, but matter as both wave and particle. Waves require a medium. All of the elements in the Standard Model are understood by physicists as excited states of the requisite fields, which can overlap and exchange energy. Change is the result of fluctuations in the field. Quantum field theory does away with what we usually think of as the most basic aspect of metaphysics, substance. Thingness is no longer fundamental, but subsumed under a more basic underlying entity, the field. The field is what's real, and all we think to be individual things are just transitive aspects of the dynamic field. Now, it's no accident that this picture bears a resemblance to aspects of Eastern thought, particularly what's found in the Hindu Upanishads. The world of things, of plurality on this view is illusory. Brahman, the underlying and unchanging reality that sits underneath and through the entire universe, is all there is. Now, the claim here is not, as was made in several popular works of the 1980s, that quantum mechanics verifies a Hindu or Buddhist worldview. But it is certainly true that many of the founding figures in the history of quantum mechanics, Heisenberg, Bohr, Schrödinger, were studying these works during the years when they were also engaged in their most important quantum discoveries. Their physical theories were reactions to physical problems using the conceptual and mathematical tools of their trade. But science, as it is produced, is not isolated from other parts of the intellectual or lived lives of those who created it. That we have a group of people reconstructing the basis of our physical understanding at the same time they're looking at alternative philosophical pictures of reality is certainly worth noting. To remove the idea of thingness from the center of our worldview can be seen as an attack on the most basic foundations of the Western view of reality, which begins with the idea of the observing subject, the self, and the world of objects which are observed. This shift to a metaphysic based on an all-present field is a move that was not lost on many beyond the world of physics. If the object is not the basic unit of being, it not only changes the basis of science, it completely undermines the basis of the visual arts. A painting is a painting of something. The great masters are those who can bring the object to life in their work, right? Whether a still life, a landscape, or a portrait, right? The painting has an object, and that object is the basis for understanding and judging the work. Do away with the object as a real thing, and you seem to do away with the possibility of painting as we understand it. As the meaning of physics was beginning to leak into the broader culture, it caught the ear of a group of artists who were interested in questions about the fundamental basis of visual art, the Surrealists. Now, we know that the Surrealists were a coherent group of artists and thinkers who were wrestling with the connection of art and reality. We know from their correspondences that they were fascinated by the advances in contemporary physics, influenced by them, and in direct conversation with people like Louis de Broglie. Man Ray photographed models of non-Euclidean figures and three-dimensional representations of four-dimensional shapes that were on display at the Poincaré Institute. Sculptures created by mathematicians to bring non-physically realizable conceptual constructs to life. Images that challenge the flat way we usually think of the world. That, of course, is what the Surrealists were interested in doing, and here we're twisting and undulating wooden and wire creations demonstrating it. By photographing them from peculiar angles, he was able to make these nerdy models appear as provocative figures, the provocative figures they really were. Perhaps the most well-known member of the group was Salvador Dali. Some of his most famous works place the artistic endeavor in direct discussion with modern physics. Consider his 1954 painting, The Disintegration of the Persistence of Memory. Now, at the top of the work, we have the famous melting watches seen in a number of his paintings. What we see is the representation of time itself, right? The movements of the hands of the watch taken from its usual solid form and made malleable. Now, in Newton's conception, time was absolute, fixed, immutable. But after Einstein, time became softer, able to be stretched and contracted. Modern science forced us to radically revise our notion of time, and that's what's symbolized here by Dali. The passing of time, coupled with human consciousness, generates memory, which we standardly conceive of as continuous. But again, the theories of modern science have forced us to reconsider that. Now the world is quantized. Continuous and smooth elements must now be thought of as discrete bundles. And so, we see in the bottom of the work, the world fading from realistically smooth to individual blocks. As one goes down from the top to the bottom of the painting, the world moves from smooth to the quantized. When we get to the bottom of the things, they are not how we think we see them. Or, consider his 1958 work, Sistine Madonna. This is a work that, perhaps as well as anything, represents the worldview of quantum field theory. Now, when viewed close up, we see a variety of gray, brown, and white spots. We see a quantized field. Stepping back a bit allows the image of the Madonna and Child to emerge from the field. And stepping back farther allows an image of an ear to come into focus. Now, the ear and the Madonna are not really the subjects of the painting. They come from the painting, but are not the objects portrayed in the way that, say, they are in Raphael's paintings. The painting is the quantized field of spots from which the Madonna and the ear emerge, but are not the objects themselves. And then there's the envelope. In the upper left-hand corner of the work is an envelope hanging in front of the painting, blocking a portion of it and casting a shadow below. Now, the first time the viewer wonders why this envelope is there and whether it's hiding something revealing about the meaning of the work underneath. Moving closer, you go to look underneath of it, and the viewer comes to realize that it's not, in fact, an envelope hanging in front of the painting, but rather is a portion of the painting. Dolly was dead for decades before I first saw this work at the Metropolitan Museum of Art in New York, but he got me good. What I thought was real, because it didn't seem to be a part of the field, and because it seemed like the things around me, the things I, in my non-scientific mindset, take to be the real world, what I thought was real turned out not to be real, just a representation contained within it. Quantum field theory and the Standard Model force an incredibly radical revision of our notion of reality. We move from a world of things to a world of fields, a world in which what there is sits underneath reality and undulates and condenses in the way that creates what we think to be things. The study of atoms has thus brought us to a very non-atomic conclusion. The uncuttable elements are indeed ultimately uncuttable in being quantized, but are not fundamental substances bouncing around in the void pictured by Democritus. Rather, they arise from space, which is itself the substance of reality.